This conference will now be recorded.
Hello everyone. We'll start with two problems that are based on VSEPR mainly it is VBT, or also there will be concept for VSEPR. So these two problems we'll discuss first, and then there will be a new theory which is molecular orbital theory, and the related parts of this theory, that is we will see how to draw the energy level for in this theory, and also bonding in some homonuclear diatomic molecules. So let's start from this problem. So in this problem we have already chosen the answer in the last class, but why the other two, that is other three that are not correct answer, that we have to understand. So for CO2 and SO2, this formula you can directly apply and you can understand what will be their hybridization. And I have already shown it that CO2 carbon atom, it is sp hybridized. You can find that using this rule of steric number, and steric number how it is related to hybridization, that table also I have already shown in the last class. Similarly for SO2 also, applying the same formula, you can understand that sulfur, that is the central atom, it will have sp2 hybridization. That means SO2 is the correct answer. But the question is why N2O and CO, these two are not correct answer, and you cannot apply this type of formula in these molecules. Remember, in limitations of valence bond theory, we have seen when there is coordinate bond present, or you can say dative bond present, then directly using this formula, you may not get correct answer. Okay, so for that, what we have to do, we have to draw the resonance structures of these molecules. So previous knowledge, if we have, then only we can apply this method. That is, you have to know first whether coordination bond is present or not. If it is not present, you can apply this formula. It is simple. But if there is coordinate bond present, then first of all you have to know its resonance structure, bonding pattern, then only you can understand what will be the hybridization. So let's take the molecule N2O. N2O, if you write the molecule, you can have this structure. Another resonance structure is also possible where this negative charge is making a double bond. So now it is O double bond nitrogen, and now there will be negative charge over this right hand side nitrogen. So it will be like this, and middle nitrogen, that is still carrying positive charge because total 4 bonds are present in the middle nitrogen. But if we want to understand how coordinate bond is present, then the second resonance structure, suppose this is the first, this is the second resonance structure will be better for you to understand that coordinate bond is present. Now coordinate bond, once again I am saying what is the difference between covalent and coordinate. So when it is covalent bond, the two electrons that are present between the two atoms, one is coming from one atom, another is coming from the another atom. But when both the electrons are coming from same atom, then that will be called coordinate bond. Once coordinate bond is already formed, then it will behave like as if it is covalent bond. But how it is formed, based on that, obviously these two are not same. So in this case, if you consider the middle nitrogen, here in the left hand side, the bond between oxygen and nitrogen, that is a single bond that you are seeing between oxygen and nitrogen, both these electrons are donated by the nitrogen. So that is why you can also draw the structure like this with this type of arrow. Fine. And there is positive sign over nitrogen because it has donated electrons, 2 electrons donated, that is according to coordinate bond. And oxygen is not using any of its valence electron, total 6 valence electron, it is still there present, but it has accepted electron from nitrogen, so that is why there is a negative charge. And in the right hand side, the triple bond that you are seeing here it is normal covalent bond, that is fine. So in this way, these 5 yellow colored electrons that you are seeing here, all these are electrons, are basically what is middle nitrogen, which out of these 5, 2 it is using for this coordinate bond. So this bond is basically coordinate bond, but these 3 bonds are normal bond. And the electrons from the right hand side nitrogen, if you see how it is using, so out of these 5, 2 it is already present as lone pair, and rest of the 3 it is used in the normal covalent bond. Okay, so what is the important point? Once you know the bonding, now you can see that the middle nitrogen, surrounding this nitrogen, there are basically two positions. Okay, so two positions are there. That means when it is two positions, as if it is steric number 2. So that is why it will be sp hybridized. Okay, and if we want to see how it is sp hybridized, so suppose after sp hybridization you have two sp and we have two unhybridized p orbital. Now these two unhybridized p orbital that will take part in pi bond formation, because here you can see there are two pi bonds, one sigma bond, this is also sigma bond. So one sp will be used for sigma bond formation, another sp also sigma bond formation, and these two p orbitals where single electrons are present, that will be used for pi bond formation. And in these two sp, one sp that is used up for coordinate bond formation, so that is you can see both the electrons are present in same orbital, another sp which is also sigma bond, but it is only one electron. So in this way total 5 electrons you can see it is present, right? So here it is sp hybridized, so that is it is not correct answer. What about CO? Now in carbon monoxide also, if you look at this bonding, what you can see here. So here between C and O there is basically total 3 bonds, but out of these 3 bonds, as you can see here, the blue electrons that are basically the electrons of oxygen and the black electrons that are the electrons of carbon. So carbon is having total 4 valence electrons and oxygen is having total 6 valence electrons. Now oxygen, out of its 6 valence electrons, it is using 1 electron for sigma pi bond, another electron for sigma bond, and this bond, as you can see, both the electrons are coming from oxygen. So that is why this third bond, which is basically coordinate bond, which is shown by this type of arrow, then this is sigma bond, and the middle one you can consider as if it is pi bond. Okay, so as it is that is both the electrons are coming from oxygen, so that is why there will be positive charge over oxygen, negative charge over carbon. And these two electrons that are not part of bonding, you can consider as if it is non-bonding. These two electrons are also non-bonding. So basically, though detailed discussion to answer this question, maybe it is not important. But remember, for CO or N2O, these type of structures where exceptions are present, that is directly predicting what will be the steric number or what will be the hybridization, it is not so direct. So that is why if you know the bonding properly, it will also help you to answer many different types of questions. Okay, so that is why I am giving some detailed explanation on the bonding of N2O and carbon monoxide. Now here, as triple bonds are present, and you can see if you consider carbon as the central atom, this is one position, this side, another position, there is basically this non-bonding electron present. So total 2 positions. So here also it is sp hybridized. Now if we want to know how the hybridization is taking place, then you can consider this diagram. So carbon, we know 4 valence electrons. Now out of these 4 valence electrons, it is 2s2, 2p2. But once this sp hybridization is taking place, now as if it is one sp, this is another sp, this is p orbital which is not part of hybridization, pure p orbital, and then another pure p orbital. Okay, similarly if you consider for oxygen, oxygen is also sp hybridized. Let me use different color. So here this is one sp for oxygen where 2 electrons are present, then another sp where single electron present, then pure p orbital where single electron present, and then another p orbital where 2 electrons are present. Now when it is come to carbon, this is actually non-bonding. You can compare it with this one. Then this sp and this sp of oxygen, these two together can form sigma bond. So you know there is a sigma bond present between carbon and oxygen. Next, this is unhybridized p of carbon. This is also unhybridized p of carbon. That means these two will be responsible for pi bond formation. And this one, which is unhybridized from the side of oxygen, and this is vacant. Now what will happen? You can understand now. Both these electrons are going to this. So this is actually coordinate bond or dative bond, and as it is donating, so you can also draw this type of resonance structure. So you will see sometimes CO is also drawn with this, and there is negative charge over carbon because these electrons are coming from oxygen. But important point is here sp hybridization is present both for carbon or oxygen. Okay, whether you consider carbon or oxygen, in both cases it is sp hybridization. So correct answer is SO2, but now you can understand all the bondings for all these 4 species. Fine. We'll go to next problem. In the next problem also, similar type of question. Specify the hybridization of the central atom in the following species. N3 minus, then we have nitrosyl chloride, that is NOCl, and N2O. Now we have already seen N2O, isn't it? It is Sp for the middle nitrogen. Now N2O and N3 minus both are basically isoelectronic species. How it is so? So for N2O, if you consider the total number of carbons, there are 2 nitrogen, that means 7 plus 7 and 1 8 from oxygen, NO. If you consider N3, then it is 7 plus 7 plus 7, all are for nitrogen. 1 more electron for the negative charge. So here also you are getting same number of electrons. Okay, it is 7 plus 7, 14 and 8. So it is 22 for both. So why I am doing so? Because if it is isoelectronic, that is also another proof that their hybridization will be same. And as you know, N2O is Sp, so N3 minus, that will also be Sp. So the first species Sp, the third species Sp, that option is present only in option A, where the first position, third position both are Sp. That you will not find in any other options. So this much, up to this much discussion, it is enough to choose which option will be correct, right? But we will also see that in N3 minus also the same type of problem, that is coordinate bond is present. So directly using the formula that we normally do to find out static number and hybridization, that we cannot do directly. So these are the resonance structures for N3 minus. This is N3 minus. 3 nitrogen atom, total overall charge is negative. Now you can see here 2 negative charge, 1 positive. That means overall 1 negative charge. Here also 1 negative, positive, 1, that is 1 negative charge extra. Same. So these 2 structures are basically equivalent. Suppose this is number 1 structure, this is 2, this is 3. 1 and 3 are equivalent. Now though this is the most stable structure, but if you want to know, or if you want to understand why that is coordinate bond, how it is present, then I will enlarge the structure. Okay, so this is 3 or 1, any of these 2 are equivalent. Now in this case, I am considering this middle nitrogen. This middle nitrogen, here out of 5 valence electron, these 3 electrons are used for bond formation with the left hand side nitrogen, and these 3 are normal covalent bond. But the other 2 electrons that are donated, that is, this is actually the coordinate bond. So you can also draw the structure like this. And that is the reason here nitrogen, there will be positive charge, and this nitrogen you can see total 6 electrons surrounding it. Now normally nitrogen valence electron 5, but there is 2 negative charge. 1 negative charge you can consider, and that is the reason there will be total 6 electrons. That is 1 electron extra. 5 valence, 1 extra for negative charge. But there is another negative charge. That negative charge you can consider because of this coordinate bond, because whenever there is coordinate bond, there is always positive charge over that atom which is donating both the, that is not do, better we say the word contributing, because donation, when we'll see, it is a different kind of situation that you can use in case of ionic bonding, where complete donation is occurring and complete acceptance is there. But in coordinate bond, better you use the word contribution. So nitrogen, this middle nitrogen is contributing both the electrons, and once it is contributed, then these 2 electrons are equally shared between these 2. That is actually coordinate bond. Once it is formed, it will behave like covalent bond. So here, in this way, you can see coordinate bond is present. But if you know the resonance structure, you can see in all these structures, basically central nitrogen, 2 positions both sides. So this is also sp. So you can you can explain it in this point of view, or you can also consider that N2 is sp and these two are isoelectronic. So N3 will also be sp. What about NOCl? Though we have reached our answer, which is option A, but what about NOCl? NOCl, now you can use this formula. So valence electron, nitrogen we will consider the center, 5. Number of monovalent atoms only 1, because Cl we will consider not oxygen. So 6 by 2, it is 3. Now when it is 3, the corresponding hybridization is sp2. So this is also matching with option A. So here option is correct option, and all the results you can see directly here. So this one, sp hybridization, central nitrogen, this is sp2, and this is isoelectronic to N3 minus, this is sp. Fine. So option is the correct option. So next theory, molecular orbital theory. In Lewis theory and valence bond theory, both this theory they can explain qualitatively the chemical bonding and molecular structure. But just like any other theory, here also both these approaches are not fully successful to describe some of the observed properties of molecules. We have already seen what are their limitations individually. Now Hunt and Mulligan introduce a more advanced theory. Basically this theory, that is will be the last theory in this chapter, compared to other theories, that is Lewis theory, VSEPR theory, valence bond theory, compared to all this theory is most advanced. Fine. So what are the key features? We know up to now what we have seen, that when two atoms are approaching each other, there is overlap between two atomic orbitals, right? Now, when atoms are combining to form molecules, suppose you have one hydrogen atom, then another hydrogen atom, and they are coming together and they are forming H2 molecule. So individually it is atomic orbital for hydrogen number 1, hydrogen number 2. But once they are overlapping to each other and they are forming this molecule H2, now their individual identity lost. So the individual atomic orbitals are losing their identity, and the new orbitals that are formed, basically that will be called molecular orbitals. So these molecular orbitals, when you will use, once the molecule is formed, now it is no longer atomic orbital. Now you have to use the term molecular orbital, that is in short MO. This is AO. Now how many molecular orbitals? See, it will always remain same. So in this case, the simplest molecule you can see, number 1 atomic orbital, number 2. So total 2 atomic orbitals, right? So 2 atomic orbitals means the number of MO, that will also be 2. So total number of molecular orbitals formed is same as the number of combining atomic orbitals. Now out of this total MO, half of this MO will have lower energy, which we call as bonding MO, represented as sigma and pi. Normal sigma sign, pi sign, that you know. But the other half of this MO, that will be considered as, that is the remaining molecular orbitals, they will have higher energy and they will be called anti-bonding MO. Now the sign is different. There will be stars, okay, superscript to sigma and pi. So half the number of molecular orbitals formed will be having lower energy, that are represented as normal sigma and pi, than the corresponding atomic orbital. That is compared to normal atomic orbital, that is before bond formation, you know there are 2 atomic orbitals for each two. Compared to the energy of that atomic orbital, Suppose the energy of atomic orbital is like this. This is one AO, this is another AO. Now you are having total 2 MO. Now half of this MO will be having lower energy, half will be having higher energy. So this is higher energy, this is lower energy, obviously compared to this atomic orbital before bond formation, right? So this will be sigma star, because in H2 there is no pi, there is only sigma, and this will be sigma because it is bonding. This is anti-bonding. Sometimes, not always. Until now, whatever I have said, sigma, sigma star, pi, pi star, that is fine. That is one half of the MO will be bonding, half of MO will be anti-bonding. But sometimes there will be some situations that there is or are some molecular orbital or orbitals, it may be one or more than one, that are having energies similar to their original atomic orbitals. So sometimes it may happen even after MO formation, just there will be some MO or MOs, that is molecular orbital or plural molecular orbitals, that will be having same energy compared to this original atomic orbital, and they will be called non-bonding MO. So bonding MO we call it as BMO, anti-bonding we call it ABMO, and non-bonding we called NBMO or NMO. Okay, so these are the three possibilities. These two always be there, but NBMO, non-bonding, it may be there or it may not be. For simple molecule you will not find it. It is in some special cases you can get it. So this newly formed MO are filled with electrons according to above principle or Pauli's exclusion principle and Hund's rule. So these three are still applied. So there is nothing new. We already know when we draw, that is, we write any electronic configuration, suppose 2s or 2p, there are certain rules. That is above principle, Pauli's exclusion principle, Hund's rule, all these we follow. When it is MO and you are filling all these molecular orbitals with electrons, then also same type of rules, they are still followed. That is as usual. Okay. There are some specific conditions that we have to maintain when we are forming these MOs starting from AO. So what are the conditions for combination of atomic orbitals? The combining atomic orbital must have same or nearly same energy. So in case of hydrogen, it is simple because both sides you have H atomic orbital. So obviously they will be having similar energy. But that may not be always. Suppose one side you have nitrogen, another side you have oxygen. That is not similar atoms. In that case, this question, that is this condition, you have to keep it in mind that the combining atoms, they should have similar energy or nearly same energy. The more similar energy, better will be the MO. If the difference is very high, then MO formation starting from atomic orbital, that will be difficult. The combining atomic orbital must have similar type of symmetry about the molecular axis, because you know in molecular axis there is overlapping occurring. So symmetry, proper symmetry must be present. So that is why you can say you will never see any bond between one s orbital and d orbital. That you will never see because of the same reason. And the combining atomic orbital must overlap to the maximum extent. Now that is not anything new. We have already considered this fact several times in other theories also. Higher is the overlap, maximum more the overlap, better will be the bond. You can say the bond strength will be very high. So the most effective combinations for atomic orbitals for formation of molecular orbitals occur when the combining atomic orbitals having similar energy. Now there is another term we will use here that we have, though we have already seen it, we know it. This is basically bond order. We already know what is bond order. But how to apply it in case of molecular orbital theory, how to calculate it, that we have to know. So bond order you can calculate once you have drawn the molecular orbital diagram, and this bond order gives you directly the number of covalent bonds. See, bond order is 3, that means 3 bonds are present. If it is 2, 2 bonds are present. If it is 0, that means no bonds are possible. And how it is calculated? It is calculated, you just have to subtract Nv, which is total number of electrons present in bonding molecular orbital. Sorry, you have to subtract Na from Nv, where Nv is total number of electrons present in BMO, that is bonding molecular orbital, and Na is total number of electrons present in ABMO. So in this way you can calculate bond order. So obviously when the number of electrons in Nb is very high compared to Na, and most of the time Nb there will be high number of electrons, and that is why it bond order negative value never possible. It is not possible at all, because whenever you will feel the molecular orbital different levels according to Abbaugh, Pauli, Kunz, obviously you will feel the bonding MOs first, because they are in lower energy. Lower energy will be filled first, and then you will, once they are filled up, then you will switch to antibond. So obviously this value of bond order, it will never be negative. Maximum you can get 0 if these two numbers are same, and it 0 means no bond. Okay, so a bond order of 0 value indicates that the molecule doesn't exist because there is no bond present. Okay, so in this way also you can prove whether bond present or not. You may get question like in suppose there are 4 species will be given in options 1, 2, 3, 4, and it will be asked in which molecule doesn't exist. So it is another way of asking, just check the MO diagram, in which case or just calculate the bond order from MO diagram and see in which case it is 0, because when it is 0 that means the molecule doesn't exist. So the question is asking which molecule doesn't exist among the given options, which is another way of checking whether bond order is 0 or not. Okay, linear combinations of atomic orbital. Basically this term that you are seeing here, linear combination, it is statistical mathematical term. Details obviously we don't need. When you will see the diagram, what it actually means, it will be clear to you. So molecular orbitals can be visualized as being made up of appropriate atomic orbitals that are provided by the atoms, which are going to form bond. A very simple, reasonable, satisfactory model is obtained if it is assumed that atomic orbital of constituent atoms, they combine in a linear additive fashion to form MO. Now what is linear additive fashion? We will see the picture within some time. So before that, just consider as if we have to consider wave function. Remember, in structure of atomic unit, we have seen this type of psi function we use for denoting wave function, right? So you have to consider 2 atomic orbitals represented by the wave function, because for each atomic orbital there is one particular wave function responsible. So if it is hydrogen atom, there will be 2 atomic orbital, first hydrogen atom psi A, second hydrogen atom psi B. But comparable energy, they are combining by linear combination of atomic orbital, and they are forming 2 MO. One of them is BMO, another one is ABMO, and that is denoted by psi bonding, a new new function, and this is psi antibonding, that is also a new function, which is for ABMO, and this is for BMO. Now how you are getting it is very simple. Psi bonding is basically when you are adding these two, and antibonding is basically when you are subtracting psi B from psi A. It is more of superimposition method where constructive interference of 2 atomic wave function produces a BMO. But if it is not constructive, if it is destructive, that is psi A minus psi B, then it will generate NBMO. So in the picture left hand side, you can see Suppose this is nuclei of first atom, you can consider hydrogen atom, very simple. And this is another hydrogen. Now when individual waves are like this, but when they are combining, and this is both are combined to each other, the amplitude of wave functions are basically added. So this is amplitude for the first wave function. This is the amplitude for the second wave function. And these two when adding, as we are adding, and this is constructive. So waves will be reinforcing each other. It is not that one wave function is cancelled by another wave function. That is not the case. They are reinforcing. Similarly, if you consider both these in the negative scale, this is positive scale side, this is negative, then also same thing will happen. Both are negative, you are doing some constructive interference, and this will generate BMO. But other possibilities, now see, one is having plus phase sign, another is having the opposite phase sign. So that is why one wave function is towards positive scale, another is towards negative. Now in this case, in the previous case, there is no node. But when this type of situation is arising, there will be formation of node where no electron density can be present. That is the definition of node we have seen in the structure of atom unit. In this case, amplitude of wave functions are they are cancelling each other. So waves are cancelling each other. This is towards positive side, this is towards negative side, and they are opposite to each other. So they will generate psi antibody. Fine. Though this is higher mathematics involved, but for this level, this much discussion is enough. Now we will see actual energy level diagram of MO. That is when it will be asked that draw the molecular orbital diagram for this molecule or this molecule. How to do it, that you will see. So as it is energy level diagram, you can see here how the energy from bottom to top, it is increasing. Now these two are isolated hydrogen atom. This is one atomic orbital. This is another atomic orbital. This is 1s orbital. This is also 1s. So when both are adding, we are getting bonding MO. Both are having same sign. Okay, so this will reinforce each other. But the other possibilities, and also important point, see, these two atomic orbital, this is the corresponding energy level. But when it is BMO, the energy level is lower compared to this level. When it is ABMO, then there will be this type of gap, that is same amount, but now it is towards higher energy side. One thing, let me check. Okay, it's fine. So one is BMO, another one is ABMO. And this antibonding MO, it will be denoted as sigma star, and this is sigma. So in this case, it is destructive. See, this is destructive interference, right? So in this way, this is the H2 molecule. Once it is formed, there will be one antibonding MO, one BMO. But mostly we do not draw the MO diagram in this way. So how we actually draw it? It is like this. So energy, it is increasing towards this direction. So in the left hand side, you have one hydrogen atom, atomic orbital carrying single electron. As we know, in 1s there is single electron. This is another hydrogen. And this is the energy level for the atomic orbital. But once this BMO is formed, sigma for 1s, because it is sigma formed by overlap of two 1s, so that is why it is written in the subscript sigma 1s. Atomic orbital of H, atomic orbital of H, and in the middle there is MO of H2, not H. The atomic molecule is already formed. And both these electrons, as we know, we in MO also we follow the same rule, above Paulus exclusion principle, Hund's rule, all these three as we follow in case of AO, here also we do the same thing. So that is why these two electrons, first you have to place both these electrons here. And once you do so, there is no electrons left. So that is why this is vacant, sigma star. You cannot place one electron in BMO, another electron in ABMO. That is completely wrong, because remember what we have said, that the three principles, that is Hund's rule, Paul's exclusion, these are always followed. And as it is lower energy, you don't think that as we do in case of normal atomic orbital, first we place, suppose this is 2s, this is 2p, and first we place one electron, and then we do pairing. So don't try to apply the same thing here. That is not the case, because it is lower energy, and we know in lower energy, once it is completely filled, then only we move to higher energy. So that is the reason you fill 2s first, and then you move, if extra electrons left, then you move to 2, because of this energy difference. So similar is the case. First you have to fill this BMO completely, then you can switch to sigma stat, and maximum capacity is 2 electrons. So that is why both the electrons are here. And if you want to check what is the bond order, remember the rule: total number of electrons in bonding MO, which is 2 in this case, total number of electrons in anti-bonding, which is 0 in this case, divided by 2. So bond order is 1, and it means between two hydrogen atoms there is a single bond. Okay, so in this way you can calculate bond order. Once you know you got the information that how many electrons are present in bonding, how many in anti-bonding. Fine. Now for H2, how it is, that you have seen. Now what about moving to the next element, which is helium. Now helium, what is the difference with hydrogen? So in case of hydrogen, it is 1s1, but when it is helium, it is 1s2. That is the configuration. So see, this is the atomic orbital of one helium. This is the atomic orbital of other helium. Both side 2, 1s2. In the middle we have MO. Now total number of electrons 2, 2, total number of electrons 4. Out of these 4, 2 we will place in the BMO, and then only we can switch to this ABMO sigma star. So in this way 4 electrons are filled. But see, if you calculate bond order, total number of electrons in bonding 2, in anti-bonding also 2, so it is basically 0. So that is the reason helium 2, this type of diatomic molecule, does not exist, which you can prove from this molecular orbital. Helium is basically monoatomic. Fine. So now the differences between BMO and MO. So it is addition overlap. Remember constructive interference. This is destructive interference. So this is, it is subtraction. In this case, what we do, psi A plus psi. But in this case, it is psi A minus psi. So it is lower viewed as constructive interference. This is destructive. So it will be ES. Then lower in energy, that you can understand from these diagrams, higher in energy. Electron in BMO shield nuclear charge between two nuclei, that is binds to nuclei, because when two nuclei are approaching each other, nuclear charge, positive charge is present, but electrons, they shield these nuclear charge from each other. As a result, this repulsion between two positive charge will not take place, and ultimately there will be bonding. Electron in ABMO cannot shield nuclear charge. Remember, in ABMO what happens? This is one wave function, this is another, so these two are destroying each other. So as a result, there is a node formation in the middle point, and because of that node, there is no electron density. So now, unlike the case of BMO, electron in ABMO cannot shield nuclear charge between two nuclei. So that is the reason now there will be repulsion, and there will be, so we call it it is antibonding. We correct it. Antibonding. Okay. nuclear density concentrated between internuclear line joining the two nuclei. In this case, nuclear density concentrated outside the nuclear line, because there is no such line. And even if you are finding these statements difficult, you can ignore it. That is because these informations are enough to understand the difference between BMO or ABMO. Last point is you can understand that electron in BMO increases bond order, because higher is the number of electrons in bonding molecular orbital, because it is n BMO minus n ABMO, then we divide by 2. But higher is the number of electrons here, obviously bond order will be high. And when electrons in ABMO is very high, that means bond order will be towards lower side, because we are subtracting it from NVM. Fine. Now different homonuclear diatomic molecules, how the bonding is occurring in MO diagram, we will see. So homonuclear means it is diatomic. So both the atoms are same, and homonuclear, same atom. So in general, you can consider it as if it is X2. So here we have B2, C2, N2. So in this way, you can also have O2, N2 like this. And you can also compare them. So that is why in the single diagram, you can see in this picture, B2, C2, N2 all are present simultaneously, so that you can compare. Now B2 single boron, if you consider, how many electrons? What is the atomic number? It is 5. That means when 2b, total number of electrons will be 10, right? Now normally in MO diagram, in the previous slide that you have seen for helium or hydrogen molecule, here we have seen AO both side, and then in the middle position we have BMO or ABM. But in this case, only this part is focused, not AO. Okay, because we are just trying to represent the picture as simple as possible. If we are doing it both sides, you can do that there is no problem. So for B, what is the configuration? It is basically 1:2, 2:2, 2p1. And when you are doing the MO, focusing on this part, that is a valence electrons part, is enough. This part, even if you do, it doesn't create, because it is fully filled orbital. So for another boron atom also, there will be fully filled 1:2. So what will happen? From 1:2 of individual boron, the MO diagram that you will get, suppose this is 1:2 for one boron, this is 1:2 from another boron. So there are 2 electrons present, and when you will have the molecular orbital diagram, it is always 2 electrons. So these two are cancelling each other. So even if you do not consider it, try to make it as simple as possible. As it is fully filled, even if you do not consider it, there will be no direct effect on the final result. So that is why just focus on this 2:2, 2p1 part. So if we consider 2:2, 2p1 part, let me draw it here. So this is 2s for one boron, this is another 2s. Here we have 2 electron, this is also 2 electron. After 2s, the next energy level, there will be 2p, right? Now in 2p, how many electrons? Only 1. And when there will be MO formation, see, this is sigma, this is sigma star. Out of these 2s, total 4 electron. So electrons will be placed in this way. Now in 2p, once you reach 2p from S, in S you cannot have any pi bond. But when it is p electron, there is a chance of pi bond also. So that is why you can see sigma 2s, then sigma 2s star. These two, this is sigma star, 2s is written because we are considering boron, carbon, nitrogen. All are from second period. So that is why 2s is written. So it is sigma star and sigma. But once you have reached p, now you also have to consider pi orbitals. So that is why first energy level wise, if you consider, first there is pi of 2p. Okay, and in pi of 2p, two lines will be there. You can also draw it like this. After that, there will be sigma. Okay, let me erase it and write it, draw it properly. So this is 2p, that is pi. After that, there is sigma. Then again, pi 2p star. These two lines you can write it like this, or you can write one by one, and then sigma star. So these are the energy level. You have to be very careful. That is, if you are drawing first sigma, then pi star, then sigma. No, it is not like that. First, it will be pi of 2p, then sigma. So these two are bonding because there is no star sign. Next is pi 2p star, and finally sigma 2p star. So this type of energy level, one by one, as it is mentioned here, this is applicable for boron, carbon, and nitrogen. Now, as it is 2p1, 2p1 both sides, so how the electrons will be placed? Now the electrons will be placed like this, which is written here in this way. So if you are using these two lines like this, one electron here, another electron here. If you are using like this, you can place it like this. So in this case, as there are two, that is degenerate level, you know, when there is degenerate level, then first you have to place one unpaired electron. Then only if extra electrons available, you can do some pairing. So in this case, maximum we have reached 2 electron. So that is why there will be no pairing. But suppose if it is carbon, so in case of carbon, it is basically 2p2. So total number of electrons 4. So in this case, once you have placed one electron in the degenerate orbitals, now there will be this third electron, fourth electron. Now there will be pairing, which you can see in case of carbon. Similarly, if it is nitrogen, now what will happen? In case of nitrogen, it is basically 2p3. So total 3 electrons will be there. Total 3 means 3 plus 3, 6. So when it is 6, after placing 4 electrons in this way, next you have to move to sigma, and you can now write these 2 electrons, because maximum capacity here for sigma, 2 electrons you have to place. Remember, in case of hydrogen, what you have done? You have placed 2 electrons, and then sigma star is vacant, right? So same type of thing here also. So in this way, you can now compare how I have drawn it in the right hand side of the slide. You can compare it directly. So in some pictures, you can find these two degenerate levels are drawn like this, or it can be also like one by one, top bottom. Both are fine. There is no problem. But whenever now why you are getting some degenerate levels? Because there is a chance of 2 pi bond formation. So as it is 2p, not just 2p, for 3p also same logic applicable. 3 orbitals. Now one orbital, if it is involved in sigma bond, these two will be involved in pi bond. So suppose it is px, this is py, this is pz. So these two will be involved in pi bond, and these two are degenerate. So that is why it is degenerate orbitals are drawn in this way. Now come to this other part of this picture. Here it is written magnetism. Whether it is paramagnetic or diamagnetic, that prediction you can directly do from MO diagram. So here you have, in case of boron, B2 molecule, diatomic B2 molecule, you have 2 unpaired electrons. So that is, it is paramagnetic. But in CT you do not have any unpaired electron. In N2 also you do not have any unpaired electron. And that is the reason it is both are diamagnetic. What about bond order? So use the formula Nb minus Na divided by 2. So for B2, these two are bonding. There is no star sign. That means 2 bonding electrons. 2 minus Na is 0. No star marked orbital, that is anti-bonding orbital. There is no electron. So 2 minus 0 by 2, it is 1. But for C2, you have total 4 bonding electrons. So now it will be 4 minus 0 divided by 2, that is, it is 2. And for nitrogen, total 6 bonded. So it will be 6 minus 0 by 2. That is why it is 3. 1, 2 and 3. So in this way you can also understand what will be the bond order. So a single molecular orbital diagram is giving you so much information for molecules. So that is, it is so advanced theory. Fine. And observe bond dissociation energy you can directly correlate, because when bond order will increase from 1 to 2 to 3, obviously now you have to provide more and more energy if you want to break the bonds, because higher is the number of bonds, that is higher is the bond order, higher will be the energy, because now you are breaking one bond for B2, it is simple. Next you are breaking 2 bonds, it will be difficult. 3 bonds, more difficult. Fine. Now these 3, that is B2, C2, N2. After that, after nitrogen, next element is, remember, nitrogen atomic number 7, next element atomic number 8, oxygen. After oxygen, which atomic number? 9. That means fluorine. So what happens in case of oxygen or fluorine, that we'll see. In case of oxygen and fluorine, the scenario is little different. Atomic number 5, 6, 7, 8, 9. So what is the difference? Again, we have ignored 1s because reason I have already mentioned. Now what is the difference? See, sigma 2s, sigma 2s star. Here also it is sigma 2s, sigma 2s star. No difference. But after that, pi 2p, sigma 2p, pi 2p star, sigma 2p star. But here that is not the case. Focus on this part. Sigma 2p, then pi bonding, pi anti-bonding, then sigma anti-bonding. So you can see energy levels are different compared to B2, C2, N2. Fine. And how the electrons are filled? For oxygen, 8 plus 8 total 16 electron. But if you consider only the valence electron, it is 6 for single oxygen atoms. So together it will be total 12 electrons you have to place. Now in 2s, you have to place 2 electrons, then 2s star, 2 electrons. Now sigma 2p, 2 electrons. Now once you have reached pi degeneracy, so now maximum capacity you have to full, which is 4. So 2, 2, 2, then 4, that means 6 plus 4, 10 already covered, 2 left. These 2 electrons, don't place it like this and then you are not putting anything. This is not correct way to do it. So as it is degenerate, first you have to place 1 electron here, 1 electron. Now you are done, 12 complete, you don't have any extra electron. But when it is F2, 9 electron, 9 electron. But if you simply consider the valence electron, it is 7, 7. 7 plus 7, 14. So see here 2, 2, 2, 4, 4. 3 into 2, 6. 6 plus 4 plus 4, 14. 14 electrons are already filled. So this is big. So here you can see some difference with B2, C2, N2. So this is very important information when you will actually solve the problem based on these molecules. So there are 2 different approaches to fill electrons for elements starting from lithium up to N2. So though lithium not shown here, but you can draw it yourself. Starting from lithium up to N2, that is starting from atomic number 3 up to atomic number N2, that is atomic number 7. There is a term we use 2s2p mixing, but details we don't need for our syllabus. Just remember this fact, because of 2s2p mixing, there is slight change in the energy level diagrams. So 2 different approaches, one is for Li2 to N2 and another is for O2 and F2. So the energy of sigma 2pzmo, why I am saying Az? Because normally when you consider sigma bond, here this bonding, sigma bonding axis is considered as Pz. It means that suppose it is Px You can also consider px for sigma, but here if you are considering pz for sigma, then sigma subscript will be 2pz, and these two you have to write pi to px and pi to py. But suppose sigma bond is formed in the axis x, then it will be sigma 2px. So it may vary from diagram to diagram. In different books also you can find different, but it doesn't matter. You just have to be sure which axis is used for sigma. So if x is used for sigma, then obviously pi will be 2py 2pz. Okay, but in this case it is sigma considered in the z axis. So the energy of sigma 2pz mo is higher than that of pi 2px and pi 2py mo in case of lithium 2 diatomic molecule up to N2. So sigma 2p, I'm simply saying sigma 2p, which is here, it is higher than the energy of pi 2px. Suppose this is 2px, this is 2pu. So this is higher, but when it is O2 and F2, you will not find that fact. Now, in case of O2 and F2, this sigma 2p, this is higher compared to sigma 2p. You can write it as Z, this is X, this is fine. So if you highlight this part of molecular orbital diagram, lithium 2 N2, then you can see. So lithium 2 to N2, sigma 2p star, then pi star 2p. Just try to focus on this part. And for O2 and F2, sigma star 2p, then pi star pi, and then sigma. So as if in between two sigma, there is 2 pi. So this is the difference. Next day, we'll also discuss some problems based on molecular orbital diagram, and then the idea will be clear. Though this theory compared to other theories, there is so many concepts, and you may find it a little difficult, but try to understand it step by step, starting from the key factors until this energy profile diagram, step by step. It will be easier for you. And when you solve problem, it will be completely clear. Okay, so we are at the end of the session. Thank you for listening.